So welcome to lecture number 12 in this course in the history of mathematics. I'm Norman Wahlberger. We're at the University of New South Wales. And today we're going to talk about non-Euclidean geometry. So we're going to skip ahead to the 19th century, which quite an interesting century. We haven't really talked very much about it at all. We skipped quite a lot from the 17th century where we were last. But this particular topic is somehow a little bit independent of the mathematics that had been going on up till that time. It sort of stands apart from a lot of other developments, and it's possible to tell you about it. It's generally considered a high point in 19th century mathematics, and it's very important because mostly it sets the stage and has great connections with Einstein's special theory of relativity. Well, actually, the general theory too. So Einstein's theory of relativity. Which, of course, is one of the great 20th century developments in science. Now, this particular topic is particularly close to my own heart. I have thought a lot about this subject in the last 10 years, and I have quite a different point of view on it from most of my contemporaries. And so this point of view is going to be influenced today by how I treat this subject. I basically don't agree with a lot of the historical judgments passed in this direction. So I have quite a different take on this, and I'll be honest with you and present the different take on this chapter. This is usually framed in glowing terms. It's one of the great achievements of 19th century mathematicians and so on and so forth. But I think a more sober assessment reveals that there's a lot of confusion and errors that were associated with this development. And some of that confusion and some of those misunderstandings are still with us today in 2011. In terms of modern mathematics, still doesn't understand non-Euclidean geometry properly. And so the physicists don't quite have the right tools to understand their theories. And I want to tell you a little bit about that. So the usual story has three main heroes. And they are Carl Friedrich Gauss, Lobachevsky, and Janos Bolyai. Okay. Now, Carl Friedrich Gauss was the dominant mathematician of the early 19th century. He took the reins after Euler and Lagrange. He was the central figure and made huge contributions in many different areas in mathematics. And he ranks only behind Euler and Newton in terms of the pantheon of modern mathematicians. It was really he who understood the existence of non-Euclidean geometry before anybody else. But for various reasons, he kept it to himself. He was a perfectionist and didn't want to publish anything until it was really perfect. And also, he was a little bit afraid of upsetting the status quo. And so he kept it to himself and never published it. And when Lobachevsky and Bolyai, a Russian and a Hungarian, when they discovered this theory essentially independently around the 1830, it became clear that Gauss had already understood a lot of what they had developed much earlier, but had kept it more or less to himself and to his students. So the story is that Bolyai had a father, Wolfgang Bolyai, who worked on geometry and worked on this famous problem of Euclid's fifth postulate. That's the parallel postulate. And I remind you that in the beginning of Euclid, he posits 5 things that we should assume that are obviously true. And the fifth one, which is a little bit more complicated than the others, asserts that if you have a line, and if you have a point that's not on the line, then there's exactly one line which goes through that point, which is parallel to the given line. And parallel means that it doesn't meet that line. There's exactly one line through that point which doesn't meet the given line. Now, to say that requires more words than any of the other postulates. The other postulates are things like, if you have any 2 points, you can always draw a line between them. If you have a line, you can always extend it a little bit further. If you have a point and a radius, you can always draw a circle. And that all right angles are essentially the same. Those are the 5 postulates. And these other 4 are reasonably easy to describe, but this one is more complicated, and people try to prove this postulate from the other 4. That was a popular thing to try to do. That goes back to Arab mathematicians were interested in doing that. And there were a whole host of people in the 1600s, 1700s, 1800s who tried to prove Euclid's 5th postulate from the other ones. And it was from this attempt that non-Euclidean geometry was born. Non-Euclidean geometry was the result of thinking that perhaps this postulate couldn't be proved from the other 4. So it was the opposite direction of what everybody else was trying to do. And Gauss was the first to really realize that this was a possibility, that it might be possible to have a geometry that's just like Euclid's geometry in the sense that these other 4 postulates are working, except that there might not just be one line through a point that doesn't meet a line, but there might be a whole range of points, or there might be a whole range of lines through a given point that don't meet a given line. There might be such a geometry. And how exactly this geometry should look was not entirely clear. But both Bolyai and Lobachevsky and Gauss started developing this geometry and seeing what the consequences of adopting this postulate are. So the new postulate is there is more than one line through a point, say A, not meeting another line, L. Now, the people who had preceded Gauss, and there's quite a whole host of them, they had tried to contradict the 5th postulate and to try to find a contradiction. So they knew that there were a couple of equivalent things to the negation of the 5th postulate. I'll come back to these other people later. So earlier researchers knew more or less that the parallel postulate, let's call it PP, the parallel postulate is really equivalent to, or pretty well equivalent to, a host of other statements. In particular, to the statement that the sum of the angles in a triangle is 180 degrees. Or 2 right angles, as Euclid would have said. So in order to prove that, Euclid had to use the parallel postulate. And eventually it became clear that the parallel postulate was really kind of equivalent to that statement. Another statement that was equivalent to was the idea that there are similar triangles which aren't congruent. There are similar triangles which are not congruent. So we all know that maybe that triangle there is maybe similar to this one, The angles are the same, but the sides are different. And that turns out to be also equivalent to the parallel postulate. And there were others like this. And at some point, the arguments would have gone, well, we reduce the parallel postulate to some other statement, which we think of as sort of obvious, and then say, well, therefore the parallel postulate must be true. Because it's obvious that there are triangles that are similar and not congruent. But Gauss realized that you couldn't really argue this way, that it might be that there is some weird geometry in which all of these statements are not true, which the parallel postulate is not true, which the sum of the angles of a triangle is not 180 degrees, which there are no similar triangles which are not congruent. So Gauss worked on this sort of strange geometry, didn't quite know what it really was about. And then Bolyai, who was the son of a friend of his, worked on it, even though his father pleaded with him not to waste his time on this. Said this is a black hole of endless toil that will not get you anywhere, because his father had spent years working on it too. And then in Russia, this fellow Lobachevsky also worked on it, and Bolyai and Lobachevsky, roughly around the same time, around 1830, Lobachevsky was actually first. Bolyai and Lobachevsky published sort of consistent accounts of this non-Euclidean geometry, where they assume this new parallel postulate, or the opposite of the parallel postulate, and show that there's a kind of consistent geometry that can be built up from it. So published this new non-Euclidean geometry. So they were both very courageous, and they were both very insightful. They were geniuses. Okay, they really deserve a lot of credit, because they went out of their way. They saw a new world, and they were not afraid of venturing out there and figuring out what's going on. But the story is really a sad one, okay, because even though they did this remarkable work, they were ignored by their contemporaries. Their contemporaries couldn't understand what it was about, and they uniformly ignored both of their works. Now the young Bolyai was very dismayed by that. He was also very dismayed when his father wrote to Gauss, who was a friend, and told him about Bolyai's achievements. And Gauss wrote back a very famous letter that says, well, that's all very good, but unfortunately I knew all of this 20 or 30 years ago. So that really devastated Bolyai. It's probably not true that Gauss knew all of that. He was probably exaggerating a little bit, but certainly he would have known the general thrust of it. So Bolyai was discouraged, and eventually sort of gave it all up, did other things. And Lobachevsky was working in a very small provincial town called Kazan, somewhere in the Soviet Union. And he didn't have a lot of support, but he kept on working. It didn't faze him too much, and he kept on going and developing his theory. Ultimately, Gauss learned about Lobachevsky's work, and the story is that Gauss purposely learned Russian in order to understand Lobachevsky's work on this geometry. Okay, so now I want to tell you, well, what is this geometry actually? All right. And here's, I guess, where I have quite a different point of view on things. But I think that this is a sad chapter in many ways. But one of the reasons it's sad is because people really there was this very easy opportunity to discover non-Euclidean geometry years and years before, and it somehow had been ignored. People got sidetracked by Euclid's 5 postulates. Instead of just asking, what's the natural thing to do? What should we really be doing here? It's hard for us to imagine how important Euclid was to these people. It was like a Bible. It really was like a religious text. So if Euclid said there were 5 postulates, then there were 5 postulates. You know, it wasn't a matter of opinion. They really took it completely literally. And unfortunately, they took it too literally instead of thinking, well, what's really going on here? If they had asked what's really going on here, they would have realized that there was a non-Euclidean geometry right in front of their nose, and it had been for millennia. Okay. There is another non-Euclidean geometry. In fact, arguably, it's the most important geometry historically. What's that? That's the geometry of a sphere. The geometry of the surface of a sphere. That is also a non-Euclidean geometry. It shares many similarities with Euclidean geometry. You can still talk about points. You can still talk about lines. You can still talk about triangles. You can even talk about distances and angles if you want. You can talk about areas. You can talk about proportions. This is in the proportion 1 to 2. And in fact, this kind of geometry had been studied for millennia. Ptolemy had studied this. All the astronomers were more interested in spherical geometry than they were in planar geometry because, as I've mentioned many times, the night sky is obviously a sphere. What goes on in the night sky is really happening in the celestial sphere, and so it's obvious that the sphere was important. So the ancient Greeks, the Indians, the Arabs, everybody had studied spherical geometry. It was an obvious non-Euclidean geometry. Why didn't they consider it a non-Euclidean geometry? Well, because it doesn't quite fit Euclid's 5 postulates. Why not? Is it true that if you take any 2 points on the surface of a sphere, there's a unique line joining them? Well, what is a line, actually? A line in this context is like a great circle. Okay. The lines are great circles. And what is a great circle? It's just the intersection of the sphere with a plane through the origin of the sphere, or through the center of the sphere. Okay, if you take a sphere and you look at the center of the sphere and you take a plane through the center of the sphere, then it will cut out from the sphere an equator, or a great circle. And those are the lines in this geometry. So the great circles are the intersections with planes through the origin, or through the center of the sphere. There's the center, let's call it O. But it's not quite true that given any 2 points, there's a unique line through them. Because if you happen to choose 2 points which are opposite or antipodal, then there's a whole family of great circles that go through them. Right? If you imagine, for example, the North Pole and the South Pole on the Earth, then all the lines of longitude are great circles passing through the North and South Poles. So there's lots of lines joining those 2 points. Okay, but if you exclude that, then there are unique lines going through points. There's another problem. What about the postulate of being able to draw a circle centered at any point of any radius? Well, if there's a point on the sphere, we could draw a circle of some small radius, maybe a circle of some bigger radius. If you keep on increasing the radius, eventually the circles that you draw kind of end up on the opposite side, and then they kind of get to a point. the opposite point, and then they kind of start coming back at you. So it was debatable whether that postulate actually held on the sphere. So because the postulates didn't quite fit the sphere, people said, no, that can't be a non-Euclidean geometry, which was wrong thinking. Of course it's a non-Euclidean geometry. Of course it's an important geometry that has to be studied. Okay, so once you understand that the geometry on a sphere is a natural and interesting geometry, then you can ask, are there any other such geometries? And once you ask that question, you are led to the other non-Euclidean geometry that Bolyai and Gauss and Lobachevsky studied. And that's hyperbolic geometry. Okay? So once you understand that spherical geometry is indeed a proper geometry, even though it's non-Euclidean, it doesn't take much to realize that there's another geometry around, and that it deserves the name hyperbolic geometry. Okay, so what is hyperbolic geometry? And I have to tell you what it actually is. But this model that I'm going to present to you today, now, was not really known to Bolyai and Lobachevsky and Gauss. They didn't think about it this way. It really is only due to the work of Beltrami. Eugenio Beltrami, an Italian geometer who really was the first person to really understand what was going on in terms of hyperbolic geometry. He was the one who brought it from, some airy-fairy, vague kind of thing to made it very explicit and said, look, this is what's really going on. And he exhibited concrete models of this geometry so that everybody could see what was really happening. Okay. And the key is to just generalize the sphere. So how do we generalize a sphere? Well, first of all, we have to represent the sphere in coordinates. In coordinates, a sphere is x squared plus y squared plus z squared equals 1. Or maybe more generally, k. If you change k, nothing much happens. The sphere just gets bigger or smaller. Unless k is 0, and then the sphere sort of disappears and becomes just a point. Or if you say k equals negative, if k is a negative number, well, then the sphere kind of vanishes altogether. There are no spheres of negative radius. But still, that's the basic equation for a sphere. And Beltrami realized that to get hyperbolic geometry, you only had to do one very, very small modification. A small but crucial modification to that formula. Okay, maybe I'll just leave that up there. Okay, that's the spherical side of things. Okay, and here is the hyperbolic side of things. The crucial thing is to look at this equation. X squared plus y squared minus z squared equals k. Just change that plus sign to a minus sign. That's all it takes to go from this non-Euclidean geometry to this non-Euclidean geometry. So what does that look like? Well, I guess it depends on what k is. These days, most people who've taken a second-year calculus course will have met these surfaces. So let me draw some of them for you. They're not spheres, of course. They're something else. What do they look like? Well, I guess the most fundamental is what happens when k is 0. When k is 0, we get a cone. That's the cone x squared plus y squared equals z squared. When k is 1, say, x squared plus y squared minus z squared equals 1. Well, that turns out to be a hyperboloid what you get when you take a hyperbola and you rotate it around the z-axis. Okay, so that's like k equals 1. It's quite an interesting surface. It's what you get if that's like the center point tower. It's a very narrow kind of hyperboloid, but it's a hyperboloid of revolution. It's a little bit remarkable because it's actually a ruled surface. You can actually draw lines which lie on the curve. In fact, if you take two planes and you draw circles on the two planes, one right above each other, and you join corresponding points here to the ones directly below them with threads, then you will get a cylinder. Okay? But then let's suppose you take that cylinder and you rotate one of the circles, just keeping the straight line straight. Well, then you'll get something that sort of looks like this. Okay, no. But if you do it, you will see that you get a hyperboloid shape like this. So that's the case k equals 1. And then there's the case k equals minus 1, which is quite different. It's also a hyperboloid of revolution, but of a different kind. So there's the hyperbola, but now we're going to rotate it also about the z-axis, so it also has sort of a circular cross-section. And there's two branches. It has two separate components. So that's the case k equals minus 1. So, okay, which one is the analog of the sphere? Well, in some sense, they all are. Okay, but Beltrami concentrated on the k equals minus 1. That's the one that sort of fit with what Gauss and Bolyai and Lobachevsky were investigating. So that thing there is the hyperbolic plane according to Beltrami. Okay, so it's some kind of analog of a sphere. And now it turns out that pretty well anything that you can do with a sphere, you can do with this surface. For example, what are the lines? What are the straight lines in this geometry? The straight lines are obtained by taking a plane through the origin. It's got to go through the origin, just as it did over here, and just cutting the surface with such a plane. Well, if you do that, you get some curve, sort of hyperbolic a little bit. Okay? You have to imagine this big cup. It's like a hyperbola rotated around. That's an example of a line. Well, it becomes a little bit hard to draw on this thing. Okay? So we'd rather have a two-dimensional point of view of this thing. And so it's like a little bit like having a map of the world. It's the same problem. How do you go from a spherical world to a planar map? The same way, how do you go from this hyperbolic world to a planar map? Well, there's several ways of approaching that, and both of them are important. So one way is to look at this world from the origin. Put your eye here and project it onto a plane that's touching the surface at that bottom point there. So we're just looking up at it from here, and for every point on the hyperboloid, we would get a corresponding point on this tangent plane. But it wouldn't go in all directions because this thing doesn't go in all directions. It kind of has a boundary. The boundary is the cone. So there's actually a circle that would be where the cone meets that plane. And the actual hyperbola that you would see would be everything inside that circle above you. So the actual geometry then is represented by the interior of that circle. And then the straight lines become just straight lines in that plane inside the disk. So that's a model. That model is nowadays called the Beltrami-Klein model. Klein investigated it too, and often called the Klein model, but it really ought to be called the Beltrami-Klein model. There's another version of it where, or there's another point of view to this looking at this hyperboloid, and that's when you put your eye down here and you look at the viewing plane, say there. It's a different picture. Okay, we're still looking up at this hyperboloid above us, but now we're down here in the z equals -1 spot, let's say. We're looking up at this hyperboloid of revolution and seeing where it cuts, seeing where our view lines intersect this plane z equals 0 now. Okay, well, you get another disk. And then you do a calculation, and it turns out that the great circles up here turn out to be circular arcs in this case. Okay? It's a different kind of view than this first one. They're circular arcs which are actually perpendicular to the boundary. And that view is the now called the Beltrami-Poincaré model. So now to tell you a little bit more about this geometry, I can dispense with a three-dimensional picture and just show you these two-dimensional pictures. Okay. Both of them are quite interesting, and both of them are naturally connected with interesting other mathematics. So maybe I'll tell you about the Poincaré model first. Okay, so here now is we're just taking this viewing plane and I'm just showing it flat out. And here is the boundary circle. Then the great circles on the original hyperboloid become lines which are actually arcs of circles. But not just any circles. The circles have to be exactly such that they're perpendicular to the boundary circle at the boundary there. So that's like a straight line in this geometry. Here's another straight line. Let's do another one. Maybe there will be another straight line. So this would be a triangle. It's a hyperbolic triangle. Now, one of the nice things about this particular model is that it turns out that the angles in this geometry are exactly the same as the Euclidean angles. So you can measure them with an ordinary protractor. Okay? So you can come along to this triangle and you sort of have to approximate the circles with lines near a vertex. You can just measure that angle, and that'll be the angle at that vertex in this triangle. You do the same thing with those things there. And if you add them up, then it turns out that the sum of the angles is always less than 180. In fact, it's 180 degrees minus the area of the triangle. That turns out to be exactly complementary to what happens in spherical trigonometry. That's not at all a surprise. If you looked at in spherical, on a sphere, then you could also have a look at a little triangle like this one, and you could also add up those angles. Then the angles are always bigger than 180 degrees. And the difference between 180 degrees and the sum of the angles is again the area. So in here, the area, no, I should say the sum of the angles equals 180 degrees plus the area. So it's very parallel to what's happening in spherical geometry. Well, what about distance? Or how are we going to measure the separation of 2 points? Well, okay, it turns out that if you were a person walking around in this plane, and we were watching you, then as you walked around, let's say you walked a little bit over here, we would notice that you've gotten smaller. And if you kept walking to the boundary, you would be getting smaller. So if I ask you, well, can you please just walk over there to the boundary? What you would do is you would walk like this way, and as you would walk, you're getting smaller, and so every step that you take is not as much as it was before. And so after an hour, you would be there. And then after a year, you would be there. And after 1,000,000 years, you would be there. Getting smaller and smaller and smaller, always walking towards the boundary. You would never get there because there's actually an infinite amount of space in this geometry. Doesn't look like it, but there is. So this blue thing is really the limit. It's not actually part of it. And this is sort of reflected if you go back to this hyperboloid model. Well, the hyperboloid really does go off to infinity. You're just looking at it. It just looks like it's sort of accumulating towards the boundary, but it really isn't. There are lots of lovely things that happen in this geometry, but I want to tell you about the other model, the Beltrami-Klein model, too. In some ways it's simpler. In other ways it's maybe not as simple because the angles don't behave quite as nicely, but the lines are straight, which is a big advantage. So let's draw the other model. So here's the Beltrami-Klein model. In this model, lines are straight. Of course, they don't actually get to the boundary. They keep going closer and closer to the boundary. So a triangle, in this case, looks just like something like this. Okay, so there's a triangle. Okay, but how do we make a ruler in this triangle? That's a natural question. How do we talk about the relative sizes between a segment over here and a segment over here? So let me show you how you do that. Actually, probably an idea that goes back to Cayley, Arthur Cayley, who was a famous British mathematician. So what you do is, let's say you have a line. Oh, there, stop there. There's a line. Suppose you have 2 points. And suppose I want to make it kind of a ruler, and I'll say that's 0 and that's 1. Where am I going to put 2? Where am I going to put 3? Okay, so here's one way of getting that. What you do is, it's like reflecting. You want to reflect 0 in 1. How do you reflect a point in 1? So what you do is you draw any line. Draw a line through O. Let's perhaps this one here. And we get these 2 points here on the boundary. And then we're going to Draw lines through here. And then we'll draw these lines here. That's going to be 2. Okay, where would 3 be? I'm going to do the same thing now. I'm going to choose 1, and I'm going to reflect it in 2. So, well, I could use, for the line through 1, I'll just use this line here. So I'm going to reflect this one in 2, and I'm going to reflect this one in 2, and I'm going to get this line here. That's going to be 3. How do I reflect 2 in 3? Well, I could use this line again. Reflected in 3, this point goes to there, that point goes to there. Join these 2 lines. That would be 4. It's actually just a straight edge construction. We could make a ruler, and if you kept on going here, you'd see that 5, 6, 7, and so on, a million, they're all squeezed in here. So over here it'd be -1, and then -2, and so on. So it's a strange kind of geometry, okay? But you can still talk about lots of geometrical things, and many beautiful things are true in this geometry. In fact, it's arguably richer than Euclidean geometry. It's more beautiful, I think. So to give you a slight sense of that, a very popular topic is the topic of tilings, regular tilings. You probably all know that in the plane, if you want a polygon, a regular polygon that tiles the plane uniformly, well, you can take a square. It's supposed to be a square, or you could take a equilateral triangle. Right. Or you can take a hexagon. Okay, if you take one hexagon, then you can build tiling, if I'm doing it right, something like this. Right, you can build like a honeycomb pattern, an infinite tessellation or tiling. And these are really the only 3 kinds. That's the planar case. What about the spherical case? Well, for the sphere, a sphere you can also tile with regular polygons, exactly the way the Platonic solids are. You take a Platonic solid, like a cube. Okay, I'm not sure if I'll be able to do this, but I'll say a cube. If you sort of put a cube put a sphere around the vertices of a cube, then you really have a decomposition of the surface of the sphere into 6 squares. And they're all the same. They're all regular squares. So it's a decomposition of the sphere, or a tiling of the sphere. So you more or less have those 5 Platonic solids and a few others that are somewhat more degenerate. But there's only really 5 plus a few more. But it turns out the corresponding picture in the hyperbolic plane is much richer. Okay? It's much richer for the following reason. Suppose you have a square. Okay, so let's say, or maybe yeah, a square is fine. So suppose we have a very small square. By a square, I mean all the sides are equal in this sort of measure, in this sort of strange hyperbolic sense, and all the angles are equal. Okay. That doesn't mean, in fact, that all the angles are 90 degrees. Okay. Okay, if the square is very small, then it's more or less Euclidean, and this square will look almost like a regular square. But because the angles don't add up to what they ordinarily do, the angles will not be quite 90 degrees. They'll be a little bit less. Now what happens if we start blowing this square up? Well, if we blow it up, I'll use the Klein model. If we blow it up to it's like that, if you make the corresponding measurement, you might find that this is now 70 degrees. These are all 70 degrees. And then if you keep on going, maybe here they're all 20 degrees. They're still, however, squares in the sense that all the sides are equal and all the angles are equal. But now the angles are not 90 degrees, they're something less. So there's this whole family of squares. In particular, you can create a situation where you have an angle of, let's say, we take 360 and divide it by our favorite number, maybe 5. 360 divided by 5 is 72. So I could cook up a square in this rather general setting where this angle was exactly 72 degrees. All these four angles were 72 degrees. Okay, and then I could create, I could sort of reflect in one of the sides here. There's a well-defined notion of reflection. So I could reflect this square in one of the sides, and then I would get another square that was exactly congruent to it. And in fact, I could keep reflecting around 1, 2, 3, 4, 5 until I got 5 different squares meeting at a single point. 5 because 72 times 5 is all the way around, 360. And I could then just carry on in all directions. 1, 2, 3, 4, 5. I could just keep making squares. They're all congruent. And I would end up getting a tiling of congruent squares where 5 meet at each vertex. And 5 can be easily replaced with 7 or 23 or any other number that you like. So there are many, many tilings in the hyperbolic plane. And I have to mention Donald Coxeter, who was the 20th century's prominent geometer, was a good friend of the Dutch artist Escher. And probably you've seen pictures of Escher's drawings. He learned about hyperbolic geometry from Coxeter. They had a correspondence. Escher didn't really have a mathematical background, but he learned enough hyperbolic geometry to create these beautiful pictures. They're called circle limit 1, circle limit 2. If you go to the internet, you can easily find them, where you have fish and various things forming beautiful patterns, all built from hyperbolic geometry. So you can have a look at that circle limit 3 or whatever. There's a whole bunch of them. You can find paintings of Escher, but they're actually not using the Klein model. They're using the Beltrami-Poincaré model. Okay, so there's a lot more to be said about this subject, but at least it gives you a bit of an idea of what the geometry is really about. It's really about a hyperboloid and various planar representations of it. And if you're interested more about this subject, well, I have a YouTube series that I've just started, which is called Universal Hyperbolic Geometry, where I explain this theory, well, a new version of this theory at great length. Or it will be at great length. There's only about half a dozen lectures so far. But there's lots of nice, beautiful aspects of this theory. And as I said, it's intimately connected with Einstein's special theory of relativity, which is, of course, a pretty interesting story too. All right, so that concludes our brief little course on history of mathematics. I will probably be teaching this course again next year, so I hope to come back and fill in some more videos in a year from now on those chapters that we haven't missed. So you can have a look every so often, every year or two, and see, catch up on some more videos. So thanks for your attention. I'll see you then.